All right, so this video is just to finish up the material in chapter 10 for you, where we really move on to the idea of mass moment of inertia, which we saw in general physics. So in this is a picture of a flywheel. And a flywheel is often used in some sort of machinery. The idea of it is that you get a large, massive object spinning, and then it can be used to drive gears to keep things moving. The reason that we show this is because it's related to the concept of moment of inertia. If you look at the way that this is built, you can see that a lot of the mass is in the outer edge of the wheel, which gives it a larger moment of inertia. This means that once we get this flywheel spinning, we can it'll keep it spinning with less work, and that's why it's useful. While this, obviously, you can look at this and say, wow, that's really rusty, this looks like old, outdated machinery. But interestingly enough, flywheels have actually been discussed as a possible way to store energy, whether you're producing energy with an alternative method like solar or wind power. One of the problems with these are that they are intermittent and not predictable. So we might have a time when we can produce a lot of energy using this method. Transferring that into mechanical energy and storing it in a flywheel is one of the ways that we can do it. So if we think about this idea, so we're introducing, this is the mass moment of inertia. We're thinking about how the mass is distributed relative to the axis of rotation. And so let's look at a really arbitrary shaped object. And here where we see is that sort of starting with the definition that we saw in general physics, is that the moment of inertia can be thought of as the sum of the mr squares, that is each individual mass, and how the radius that they are located away from the axis of rotation. For a solid object, we would change this into using incremental pieces of mass times r squared, and instead of doing a summation, we would be adding it up via integration. The units of mass moment of inertia is going to be either kilograms meters squared, or if we use our units of measurement, remember we use slugs to measure mass, and the distance would probably be feet. So it would be slug feet squared. Just like we saw with our moment of inertia that we covered today, we have a parallel axis theorem for mass moment of inertia. It's actually basically exactly the same as what we found with the area, but here we see we're still finding the moment of inertia about an axis that is parallel to an axis passing through the object's center of mass. Here you can see in this picture we have the axes. The primed axes have their origin located at the center of gravity, which is probably going to be the same as the center of mass. If we knew the moment of inertia when the axes were located that way, that's what the IG would be. But we want to move the axis parallel, a distance d, from the original location. Then we would just take the moment of inertia with the axes through the centroid, or the center of gravity, and then add to it a term that's equal to the mass of the object times the distance squared, where the distance squared is the distance that we've moved the axes. So we'll look at an example where we use that. I didn't really talk about it in class today, but there was a slide about the radius of gyration. If we end up finding the moment of inertia for an object, we can actually write it as a mass times a quantity squared, which is going to be a distance, and this is what is called the radius of gyration. The idea is that we imagine, so if I have a certain moment of inertia, we could think of what would be the appropriate distance from the axis of rotation that I could locate all of the mass and have that same value of moment of inertia. That distance, which is here shown as k, is called the radius of gyration. Similar to what we did with composite bodies for moments of inertia when we're using areas, we can use the parallel axis theorem to find the overall moment of inertia of a composite body by just finding the individual moments of inertia of each piece, if necessary, using the parallel axis theorem to find these values, and then adding them together to get the overall moment of inertia. Okay, so I wanted to look at an example of how we might do an integration for the moment of inertia, and in this one I'm going to do it in a particular way. So this is sort of a solid of revolution where we are taking the curve y squared equals x. We're revolving it around the y-axis to form a three-dimensional object, and we want to find the moment of inertia about the y-axis. So it actually says to find it using the DIY. So we're doing this. This is similar to what we did in some of the exercises today, DIY. And you might say, the idea is that this little element here has a certain moment of inertia. It's like a contribution. Now, how would I know what that is? Well, this thing is called, it's a disk. That's what that shape looks like, right? I've taken a little element of this. It actually is an element of volume, but it also could have a certain small contribution of moment of inertia. I can remind myself the moment of inertia of a disk is 1/2 mr squared. And so the DIY would be 1/2 dm times r squared. And the dm is 1/2 the density times the dv. This is the element of volume. Times r squared. So that's how I'm going to write, or what I'm going to use to help me write the moment of inertia DIY. So I'm using this idea that I got right here. I have 1/2 rho dv r squared. Now, let's tackle dv first. How would I talk about how much volume this has? Well, it's a disk, so the volume of the disk would be the area of the circle times the height. The area of the circle would be pi r squared. But in this picture here, this is my radius. The radius could be measured in terms of x. So I might want to write, I would want to write that. The height, I should do this first. The height is just going to be dy. Now, going back to the radius is measured in x. So I'm going to call this pi x squared. And then the height is dy. I see that this dy indicates I'm going to integrate over y. So I need to change this, write this in terms of y. So I have pi, well, using this equation, x squared would be y to the 4th dy. So this is how I'm going to write dv. This is my dv. And I'm going to continue on the next page so I have a little bit more room. did a couple things. I kind of rewrote some of the stuff I had on the previous slide just as a reminder for us. I did input the value I had found for dv, which this was our dv. I left the r squared as it was just to rethink that again. Remember that I'm saying this is my radius, which is actually the x coordinate. So if I square it, it would be x squared. But x squared, x is equal to y squared, and then I square it, so I get y to the fourth. So this is actually, I got a lot going on here. This is rho pi, and my integral is y to the eighth dy, and y goes from 0 to 1. And here I have 1/2 rho pi y to the ninth over 9, evaluated at 0 and 1, which just gives me a 1/9. So I have 1 over 18 rho pi. And so I already know what rho is. I was given a value of rho, and so I can say I is equal to 1 over 18 times 5 times pi. So it's 5/18 pi, and it would be measured in slugs feet squared. All right, so that's how I found the value for the moment of inertia about the y-axis. Okay, here's a quick little exercise using the parallel axis theorem. So I have a composite object. I'm doing two things, the composite object and the parallel axis theorem. So the composite is made up of a rod, which is I'm going to call object number 1, and a sphere, object number 2. The total moment of inertia will be equal to I1 plus I2. I am given some of the dimensions of the rod and the sphere here, like their mass. And then on the picture gives us some other dimensions that I need to know. Now I1 is the moment of inertia of the rod. The moment of inertia of the rod when the axis goes through the center is 1/12 ml squared. Using the parallel axis theorem, I've moved the axis from the center to the edge, which is L over 2 is the distance. So I have m and then L over 2 squared. So I have ml squared times 1/12 plus 1/4, which is equal to 1/3 ml squared. So you might say, why didn't I just write that? Because we used this result a lot. We probably knew that the moment of inertia of the rod about its end was 1/3 ml squared. But it doesn't hurt to just practice using the parallel axis theorem. All right, let's put in values. So the rod has a mass of 10 kilograms. It has a length of 450 millimeters. I'm going to change this into meters. And I get a moment of inertia of 0.675. This is going to be kilograms meters squared. Now we do the sphere, I2. The moment of inertia of a sphere with an axis through its center is 2/5 mr squared. And then we would add the distance that it is moved, that axis. So here, this is the distance for that the axis of the sphere has been moved from here to here. So we got 2/5. The mass is 15 kilograms. The radius is 100 millimeters. Then we have 15, and then that distance is 0.55. And this ends up to be 4.598, and we add these together to get the total moment of inertia. and we get 5.273 kilograms meters squared. All right, so that's it for mass moment of inertia. We don't use it a ton, but it doesn't hurt to flex some of your integration muscles or using parallel axis theorem.